All right, so what's the relationship between impulse and change in momentum? Well, we're going to use Newton's second law to show this. Net force is going to be equal to mass times acceleration. Now, if you remember the equation for acceleration, acceleration equals change in velocity over time, which is final velocity minus initial velocity divided by time. So we're going to plug that in for acceleration. And we get that the mass is being multiplied by acceleration, which is final velocity minus initial velocity divided by time. We go ahead and multiply both sides by time, and we get net force times time, which, if you remember, that's going to be impulse. That equals mass times quantity, final velocity minus initial velocity. Distribute that mass to both of those, and you get that net force times time equals mass times final velocity minus mass times initial velocity. Now, the impulse is net force times time. The mass times final velocity minus mass times initial velocity, that's change in momentum. So impulse is going to be equal to change in momentum. Now, this is a third way to find impulse. The first way was to use net force times time, which is written right here. The second way was to find the area under a force versus time graph. That'll give you impulse as well. And the third way here is going to be to find the change in momentum. If we can use this to find the change in momentum, that will tell us how much impulse an object has. All right, so what are the applications of impulse equal change in momentum? How does that actually affect real life? What are the concepts behind it? All right, so for the first one, if we want to stop and you have some mass with some initial velocity and it's going to have a final velocity of 0. Oftentimes we could think of a car wreck or something like that. How do you decrease the amount of damage in the process? Because what happens is any object that's moving in a car wreck usually is going to stop by the end of it. So how do you minimize the damage? And really we're not really worried about the damage to the car as much as we're worried about the damage to the people inside the car. So with this video, what I'm going to show is I'm going to show how this cart right here is going to hit the force sensor, and then that force sensor is going to read the amount of force and the amount of time that that force is in contact. So let's take a look at the first one. You can see as the cart moves, it's going to hit that force sensor and bounces back a little bit. And then we look at the force versus time graph, you see the amount of force that's being applied and the amount of time that's given. So this is the force. You can see the force peaks pretty high, but the amount of time that's in contact is actually very small. So next I'm going to take the cart, I'm going to turn it around, and I'm going to have the plunger actually hit the force sensor, which means it's a little bit softer. You can see it's a little bit softer hit as the two collide together. And then if we look at the force versus time graph, we see that the force actually is a little bit smaller, but you'll notice that the time is wider. So effectively what we're looking at is we're looking at the force being decreased by increasing the amount of time that the two are in contact with each other. So if we look at the two graphs, we see that the height, which is the force, and the width, which is the time, if we multiply those together, we get the area of this little graph right here, and then we get the area here. You can see, if you can imagine, these two areas are about the same, which means that the two carts had about the same impulse. But damage is not determined by how much impulse an object has, it's determined by how much force an object has. So basically with the hard stop without the plunger, you get a very short time that the two are in contact with each other, but you get a very large force out of it. And with the soft stop, with the plunger, that kind of softens it a little bit. You increase the amount of time that the two are in contact with each other, which decreases the amount of force. And that's essentially how all safety equipment works. Basically, it decreases the force by increasing the amount of time that the two are in contact with each other. So how do we minimize the damage in a car wreck? Well, think about this. Damage is related to the amount of force that's being applied to your body. So how do we minimize the force? Because in a car wreck, you can't really, while you're in the wreck, you can't change anything about the initial velocity. You're going to stop at the end, so you're going to have a final velocity. The mass of the car is set as well, so the total change of momentum, everything on the change of momentum side is set in stone. There's nothing you can do to change that. But what you can do is since impulse equals change of momentum, what you can do is you can decrease the amount of force by increasing the amount of time. Since change of momentum equals net force times time, which is impulse, then the change of momentum is the same on that side of the equation. Then to decrease the force, you increase the time. It's referred to as being inversely proportional. So if you increase the amount of time that you're in the wreck, that'll decrease the amount of force. Now there are a couple of things, a couple of designs in a car that does this. airbags. What it does is it stops your body from moving forward over a given period of time. Rather than hitting the dashboard and stopping in an instant, you're going to hit the airbag, and it's going to take, a little bit longer to stop, and that means you have more time to stop, so you're going to have less force being applied to your body. Also, there are crumple zones on the car. The purpose of crumple zones is to add a little bit of distance between you and the other car, so as the car is crashing into you, there's a distance that it can crush, so that it increases the amount of time the two objects are colliding and decreases the amount of force. Some cars even design the engine that when they get in a wreck, the bolts that hold the engine in shear off, the engine drops down, and that gives the entire hood, the distance of the hood can crumple up, and that gives even more time for the car to stop, which it translates over to less force being applied to your body. All right, the next thing is rock climbing with a nylon rope. Now, the purpose of a nylon rope, as opposed to a very stiff rope, nylon actually stretches some, and so when you fall and the nylon rope catches you, you fall over a distance. So the nylon rope stops you in a longer period of time than the stiffer ropes. So in that process, what it does is it decreases the amount of force being applied to you, while it increases the amount of time that the nylon rope stops you. The next is getting hit in boxing. If you've ever watched boxing, you may even notice that the boxers will actually turn their head when they get hit in the face. They will turn their head with the punch, and what that does is called riding the punch. And what that does is that increases the amount of time that the other person is in contact with their face, and by increasing that time as they turn their head, that decreases the amount of force of the punch. Okay, so what do they have in common? Well, they have in common that the change of momentum is constant no matter what you do, but the impulse side of it is going to be constant as well. So minimize damage, which is force, you have to increase the amount of time that the force is in contact. By increasing that time, you decrease the force, because this side of the equation here, the change of momentum, doesn't change. All right, so we have a demonstration in class where we have a happy and sad ball. The happy ball is a bouncy ball. The sad ball just kind of hits the ground and stops and doesn't bounce back. And the question here is, which one is more likely to knock over a wall?
I want to take a second and I want to talk about this demonstration with the happy and the sad ball. So just to give you an idea of why it's called the happy and sad ball, let me show you what happens here. I take the happy ball and I drop it. Gives me a bouncy, what referred to as elastic collision. This being the sad ball, it just stops and gives us an inelastic collision. So again, the happy ball and then the sad ball are elastic and inelastic collisions. So what I'm going to do is I want to look at how these two affect the this wall in trying to knock it over. Okay, so I have my rod here that serves as a reference in order for me to see, just make sure that each one of these, as I lift them up, I'm going to lift them up to the same height so they reach the wall with the same velocity. And if they reach the wall with the same velocity, then that's going to be a constant between them, and their bounciness should be the only thing that affects whether it knocks it over or not. Okay, so let's start with the sad ball. Doesn't knock it over. Now let's try it again, except this time with a happy ball. And you can see that it does knock it over. Again, let's try the sad ball. And then the happy ball. So the only difference between the two is whether they're elastic or inelastic. So let's talk about why this is the case, why the happy ball will knock it over, but the sad ball does not.
And if you look at the two, you say, well, maybe the sad ball hits because it'll knock it over because it hits it pretty solid. It seems like it would knock it over. But when you think about it, think about change in momentum. If the sad ball just hits and stops, and the happy ball hits, stops, and then goes back the other way, which one is harder to do? Which one has a greater change in momentum? Because the sad ball just stops, well, the happy ball just stops too, but then it goes back the other direction, which means it's a greater change of momentum, which means it'll deliver more impulse to the wall to be able to knock it over. So with a greater impulse, because it does go back the other direction, it is going to deliver more impulse, and the happy ball is going to knock over the wall more than the sad ball is.
So next the question may come up, well, why don't we make wrecking balls that are more like the happy ball than the sad ball? It would only make sense that something that's more able to knock over a wall would be better material to make it out of. So why don't we make it out of bouncing material? So it seems like a wrecking ball is pretty solid and doesn't bounce. But what's interesting about a wrecking ball is a wrecking ball, generally speaking, is made of steel. So here's an example of a steel ball. And if you see the steel ball, if I drop it from this height, it actually does a pretty good job of bouncing. It actually acts more like the happy ball than it does the sad ball. So just to give you a reference, I'm going to actually drop the happy ball and the steel ball at the same time from the same height, and you can see how bouncy it actually is. It's actually about as bouncy as the bouncy ball. So the fact of the matter is that wrecking balls actually are made of materials that act more like the happy ball than the sad ball, so that they can knock down walls.
All right, so when you have a wrecking ball, you would want a wrecking ball out of a more elastic material, something that's going to bounce more. Now, if you think about this, you think about wrecking balls, they're made of steel, and you don't really think of steel as being something that is very bouncy. But in fact, if you've ever seen a steel bearing or steel ball and you drop it, it actually bounces pretty well. It's actually fairly elastic. A wrecking ball made of steel acts more like a happy ball than it would a sad ball. All right, so this is more of an elastic collision to bounce, and an inelastic collision is more of the sad ball, which just hits and stays where it is. So why is cork and bats against the rule in baseball? Well, the cork inside the bats, what it's going to do is it's going to allow the bat to compress more, and by allowing it to compress more, it makes it more like the happy ball, so it delivers more impulse to the baseball than it would be if it was solid wood. So the cork is easily compressed and allows the rest of the bat to compress with it. If the bat is able to compress more, the bat acts more like a happy ball than the sad ball, and this allows a change of momentum that's greater to the baseball, and that gives an unfair advantage to the team that's using it. All right, so let's say we have this guy who is he has a fan that's blowing into the sail here, and we could see by the cartoon it looks like it's actually causing the boat to move forward. Now, is this obvious? Does it make sense that the fan would cause the boat to move forward? Well, consider this: the fan is being held by this guy, which is attached to the boat, and then you got the sail that's also attached to the boat. So basically, you got wind being pushed on the fan. As the wind goes forward, it's pushing the fan to the right, and then when the wind hits the sail, it pushes the sail to the left. Now the fan and the sail are both a part of the same boat, so you got two forces that are in opposite directions. You've got the fan to the right, and then the sail is being pushed to the left. So the question here is, which one is greater? Which one causes more force? Which one's going to win? Okay, so we're going to look at this demonstration where we have a fan that is attached to a boat, and this fan is basically being pushed to the left. Now the reason for this is because when the fan turns on, it pulls the air that is on this side of the fan through the fan, which means that the air is being pushed to the right, but by Newton's third law, that means that the fan is going to be pushed to the left. So there's an impulse on the air to the right, but there's an impulse on the fan to the left. Now let's look at it when we have a sail that is here that is curved actually towards the fan. Now what does that mean? Well, what's going to happen is the fan's going to push the air through, but the air is not going to just move completely to the right. There's a sail here that the air is going to hit. So the question is, the impulse that is acting on the fan that's pushing it to the left, and then an impulse of the sail that's pushing to the right, which one of those is going to be greater? Is it going to be more on the fan? Is it going to be more on the sail? Or is it going to be the same on both of them? So we go ahead and attach the sail. Notice that the sail has a little bit of curvature to it, and that's actually going to be important. You see that the curved side is going to be facing the fan when we put it into the boat. Now when we turn the fan on, then that means that the air is going to hit the fan, but then the curvature actually allows the air to move back the other direction. So there's a net impulse that's actually going to be acting on the sail rather than the fan. So we know there's an impulse on the fan because it pushes the air through. We know there's an impulse on the sail because the air hits that sail. But we can see that there's going to be more impulse on the sail than there is on the fan. Let's talk about why this is. So the air that gets pushed through the fan pushes the fan back to the left. So there's a change in momentum of the fan. There's an impulse that's acting on the fan. Now the air that hits the sail doesn't just stop. So let's talk about the change in momentum. The air goes from essentially zero velocity to some velocity when it goes past the fan. Now when it goes past the fan, it hits the sail, it doesn't just stop, it actually goes back the other direction. If it stopped, it would be the same change of momentum because it would go from zero velocity to some velocity, then that same velocity back down to zero, that would be the same change, one positive, one negative. But since it actually goes back in the other direction, then that means the change of momentum at the sail is actually greater. So with a greater change of momentum at the sail, that means more impulse is acting on the sail than is acting on the fan. So again, with more impulse acting on the sail than there is the fan, then that means the net impulse is going to be to the right on the boat itself. All right, so what if we turn the sail around? Now the sail is facing such that the curve is away from the fan. What happens in this instance? Well, again, we have the air that's going through the fan and it has an impulse on the fan, but instead of stopping and going back the other direction or just stopping in its place, it actually will keep going in the same direction. All right, so let's look at what happens in this instance. All right, so we have our sail. We're going to go ahead and flip it around so that the curve is now the other direction. So let's look at what happens in this instance. We turn the fan on, and we see that the net impulse is actually to the left, which means that there's more impulse acting on the fan to the left than on the sail to the right. Okay, so let's talk about why there's more impulse on the fan. So this time we have the air going through the fan just like we did before. So there's a change of momentum that is happening to the air and thus an impulse that's happening on the fan. However, since the air doesn't go back the other direction, it actually keeps going in the same direction, which means it kind of just slows down a little bit. So the impulse that's acting on the fan is going to be more because the air goes from essentially zero velocity to some velocity to the right direction. But then that air only slows down. It doesn't stop completely. So that's less change in momentum, which means less impulse that's acting on the sail than is the fan. So with less impulse on the sail, that means more impulse on the fan, and the net impulse is going to be to the left. So again, with more impulse on the fan than on the sail, then that means the net force is going to be to the left. Of course, it'd be easier if we just take the sail off and let the fan do what it does. It would push to the left more so. So what if we have a flat sail? What if we completely leave it flat so that the air doesn't go back the other direction, nor is it able to keep going a little bit in the same direction and only slow down? So let's see what happens here. All right, so you see with the fan on and the curvature toward the fan that the net impulse is going to be to the right. Now, if we go ahead and add our piece of paper in between the fan and the sail, then what we see is that the net impulse is going to be zero. So that means that the impulse acting on the fan is going to be the same as the impulse that's acting on the sail. Let's talk about why this is. All right, so we have an impulse that's acting on the fan, same change in momentum. The air goes from zero to some velocity. But when it gets to the sail, it doesn't keep going forward, nor does it keep going back. It actually gets pushed up and down and out to the side. Now, momentum is a vector, which means that even though it's still moving up or still moving down, the forward motion is zero. So if the velocity of the air goes from zero to some velocity, and then that some velocity back to zero in the horizontal direction, then that means the change of momentum before it goes through the fan, or as it's going through the fan, is going to be the same as the change of momentum as it hits the sail. So with those two changes in momentum being the same, then that means it's going to be an equal impulse on the fan and on the sail. So with equal impulses, that means the net force is going to be zero, and that means there's going to be no acceleration. It's not going to be pushed to the right or to the left more so.